This is the last of the friction videos, and in this video we're going to try the third level of problems in terms of friction. So the very first level or type of problem we had was we were putting with a force horizontal to a surface, and in this example we could just say that the weight of the box was equal to our reaction force because we had a parallel force being pulled across a flat surface. In the second type we had an inclination, let's say of 20 degrees, and in this example we had a weight force going down, and so in here our weight was not equal to our reaction force because the reaction force being perpendicular to the surface was the amount of weight going into the surface, not the whole weight itself. In this third problem what we see is we're going to have some sort of angle, let's say 30 degrees, that the object is being pulled at. So instead of being pulled horizontally, it's being pulled at an angle. And in this example, again, our reaction force is not equal to the weight, because what happens here is we actually lift the object up slightly when we're pulling it. And it means that our weight component does not equal the reaction force. So that's what makes both problem type 2 and problem type 3 a little bit more difficult. And that's what we're going to be focusing on today. So I'm going to give you a quick example. Here's an object. It weighs 147 newtons, and by the way, this comes from the Copeland text, Engineering Studies Definitive Guide, and it's in example 2.2. But looking at this problem, what we see here is we can't say that the reaction force is equal to some value or 147, because the vertical part of P, or P vertical, is actually lifting up some of the box, and P horizontal is the amount that's actually pulling the box along that surface. And so reaction force in this example is not equal to our weight. Alright, we still have our normal equation for friction and our reaction force, which is true, but in this example the only thing that we do know, which is given in the problem, is that mu is equal to 0.25, and we know that the weight is 147. So we know neither the frictional force nor the normal reaction. And so it leaves us a little bit stuck because we don't have a lot of knowns. What we'll have to do is go back to what we understand about the sum of the forces in the vertical components, which all must equal 0. And if we look at this problem, we see that the vertical forces are P vertical plus Rn, which is our reaction, minus our weight. So our weight pulling down, our reaction, and our P vertical. And let's put some numbers into that. So 0 equals, well, the vertical component of P in this example, being a 30-degree angle, is going to be equal to sine P sine 30. So if that's the value P sine 30 is equal to our P vertical plus our Rn, well, we don't know it, it's not equal to the weight, minus, well, we do know the weight, 147. So the only thing we do know here is that that's equal to 147. So I guess if we put something down here, Rn is equal to 147 minus P sine of 30 is the answer, and sine 30 is 0.5, so 0.5p. So let's write that nice and neat. 147 minus 0.5 times p. And what we see is that that's got two unknowns, p and an Rn, so that's just becoming our first equation. We can't go any further than that. We now look at the sum of the forces in the horizontal. They must also equal 0. What are those forces? Well, the only forces that we have are the horizontal part of P and our frictional force, F. So those two forces are the forces acting horizontally. The cool thing about F is that we can write F as a function of coefficient of friction. So FF is equal to mu times Rn, and P horizontal we can write as its component of P. So P horizontal is E times cos of 30 degrees minus FF is mu times Rn. And so now what we see is we've got two equations, and this is equation 2. Two equations with two unknowns, Rn and P. And what we can then do is say, well, we can substitute one unknown from here into this equation so that we've only got one unknown in the equation. So what I'm going to do is say, well, if Rn is equal to 147 minus 0.5p, I'm going to substitute that over here. So I'm going to put this Rn and replace the word Rn here with what it's equal to. So it's going to be P times, and let's just go cos 30. Cos of 30 equals P times 0.866 minus coefficient of friction 0.25 times Rn. And instead of writing Rn, I'm going to use 147 minus 0.5p. I'm just substituting that equation into this equation, and so what I see here is that it's equal to 0.866p minus, and we start doing some of the maths here, and what we'll see is, let's get our calculator out, 147 times 0.25 is 36.75 minus 0.25 times 0.5 equals 0.125p. And going along with it, more of our math, 0.125 plus 0.866 equals, so p times 0.991 is equal to, I'm just grouping these two values together, adding them together, and then putting them all across the other side, is equal to 36.75. So P is equal to 36.75 divided by 0.991, which is equal to 36.75 divided by 0.991, 37.08 newtons. So what we see is by substituting one equation into another and then having to do a little bit of my normal maths, I can get to the value of P. What I can't do in this problem is I can't just jump to the conclusion that Rn is equal to my weight force, because we see that the vertical part of P is actually taking some of that weight.